Om Swastiastu. Assalamualaikum warahmatullahi wabarakatuh. Salam Nama Budaya. In this video I will explain about chapter 9, that is Metallurgy for the Non-Metallurgist. But the first I want to introduce myself. My name is Putra Hutabarat with student ID number 2305531 I am from Mechanical Engineering study program from Engineering of Fakultas and Udayana University. Okay, chapter 9, heat treatment of steel. Heat treatment is the controlled heating and cooling of a solid metal or alloy with methods designed to change the microstructure to obtain certain properties. Heat treating is carried out below the solidus temperature of the alloy, and the purpose of heat treatment is to change the microstructure and properties of the alloy. The ability to change properties by heat treatment has contributed greatly to the usefulness of metals and alloys in a wide range of applications, from sheet metal for automobiles and airplanes to razor blades and tool steel. 9.1 The iron carbon system. Carbon is crucial in heat treatment as it widens to the temperature range for austenite stability and lowers the temperature needed for austenation in steel. Austenation determines steel properties, and it is used in various heat treatment processes such as annealing and quench hardening. Next, carbohydrates are most insoluble in ferrite because the available interstitial positions in the BCC lattice are not large enough. However, carbohydrates are more soluble in austenite because the largest interstitials in the FCC lattice are better able to accommodate carbohydrates. The solubility limit of carbon in a ferrite varies from 0.008 with Wt% at -18 degrees Celsius to a maximum solubility limit of 0.022 Wt% at 727 degrees Celsius. However, the maximum solubility limit of carbon in austenite is about 2%. When steel is quenched from the austenitic phase to room temperature, different phase transformation occur. Carbon is trapped in the ferrite lattice, causing the composition to rise above 0.02% dissolution of carbon in ferrite. This causes lattice distortion and martensite formation. Martensite has a very hard BCD crystal structure and is the basis for hardening steel. Next, 9.2 Common phases in steel. Heat treatment of steel requires an understanding of both the equilibrium phases and the stable phases that occur during heating and or cooling. For steel, the stable equilibrium phases include ferrite, austenite, graphite, and to some extent cementite as a very stable iron carbide. 9.2.1 Cementite and perlite formation. True eutectoid steel consists about 0.77% Celsius. When the steel reincarnates slowly below 727 degrees Celsius, the ferrite and cementite phases separated almost simultaneously to produce a microstructure called perlite. This name comes from Sumber research. Yes. Ferrite tends to grow along the austenite grain boundaries. When the eutectoid temperature is reached, the remaining austenite transform into mixture of ferrite and cementite with the distinctive lamellar bands or parallel parasites between the boundaries of the so-called protected ferrite, picture 9.58. Next, hyper-eutectoid still have a carbon content greater than the eutectic composition of 0.77 Wt percent Celsius. As the dissolved carbon increases in austenite, the iron atoms are pushed further apart. This stretches the semi-compounds, and there is a limit to how much strain energy the austenite can withstand. Ultimately, cementite forms in austenite when carbon exceeds the solubility limit. Next, 9.2.2 martensite. As a note, martensite is a metastable structure that forms during rapid cooling of austenite. Unlike the isothermal decomposition of paste constituted by diffusion, martensite is not a paste associated with thermal equilibrium. Thus, it does not appear on the iron-carbon equilibrium paste diagram. Martensite in alloys has an acicular microstructure. If solute atoms occur in interstitial positions, it is hard and strained. If they occupy substitutional positions, it is soft and ductile. Carbon content affects the hardness in steel. Martensite is less densely packed than austenite and ferrite. Alloying elements have an influence on tempering response, with certain elements being more effective than others. Elements like nickel, silicon, aluminum, and manganese act as solid solution strengtheners and do not greatly hinder softening. On the other hand, elements like molybdenum, chromium, vanadium, niobium, and titanium, which form metal carbides, effectively slow down softening during tempering by inhibiting the coarsening of iron carbide. The slower diffusion rate of carbide forming elements help in maintaining the fine dispersion of carbides, resulting in a slower softening rate at higher temperatures. Next, 9.2.3 bayonet. Bayonet is a metastable paste in steel that forms when cooling is not fast enough for martensite, but still prevents carbon from diffusion to form perlite. Unlike perlite, bayonet has a acicular ferrite and discrete carbides, giving it different properties. Bayonet still have strength and toughness, while perlite still have strength but poor toughness. Bayonet and sour cores found a temperature range where perlite and martensite won't form, but a new structure called bayonet does. The bayonet transformation occurs below a certain temperature, allowing the mapping of structure in the paste diagram. 9.3 Critical temperatures and transformation diagrams. The critical temperature of steel defines either the onset or completion of a paste transformation. Three important critical temperatures in steel heat treatment are: A1, critical temperature for the start of the transformation to austenite, and the so-called eutectoid temperature. Critical temperature A3, critical temperature for complete transformation of the A+2 paste mixture into 100% austenite. ACM, critical temperature for complete transformation of the G plus Fe3 paste mixture into 100% austenite. Transformation diagrams. The kinetic aspect of paste transformation are as important as the equilibrium diagrams. For the heat treatment of steel, any practical heat treatment requires heating and or cooling. Therefore, another important tool in steel heat treatment is the use of transformation diagrams that plot phase transformation as a function of temperature and either time or the rate of temperature change. Next, still heat treatment methods often rely on the use of TTG diagram, which were developed by Pate and were the basis of understanding the conditions of beneath formation in steels. However, continuous cooling diagrams are very practical tools in heat treatment. Continuous cooling diagrams plot phase formation as a function of cooling rate at picture 9.22. 9.4 Annealing or normalizing. Heat treatments are not limited to just hardening and tempering. Various annealing methods are useful in developing more uniform microstructures and other combinations of properties such as ductility, formability, and machinability. General annealing thermal cycles. Annealing cycles are varied according to the temperature and the method of cooling used. Subcritical annealing does not involve the formation of austenite. The prior condition of the steel is modified by such thermally activate processes as recovery, recrystallization, grain growth, and agglomeration of carbides. Next, full annealing. The temperatures for full annealing are typically 50 degrees Celsius, or 90 degrees Fahrenheit above the upper critical temperature A3 for the high or hypoeutectic steels and the lower critical temperature A1 for hypoeutectic steels, picture 9.23. It is referred to as a full annealing because it achieves full austenation of hypoeutectic steels. The indicated temperatures for fuel annealing are a supercritical anneal for hypoeutectic steels, but are in the range of an interstitial anneal for hypereutectic steel. Full annealing produces microstructure that is softer and more amenable to other processing such as forming or machining. In addition, stainless and high alloy steel may be austenitized, fully annealed, and quenched to minimize the presence of grain boundary carbides or to improve the ferrite distribution. The temperatures for fuel annealing are in approximately the same range of austenitization temperatures for water quenching, picture 9.24, but are below austenitization temperature for either normalizing or hardening by oil quenching. Next, 9.5 Types of annealing treatments. Annealing are at supercritical temperature below AC1 consists of three temperature regions. Stress relief annealing, where structures are uniformly heated and cooled to relieve internal strain energy through this location rearrangement without altering grain shape. Recrystallization annealing replaces deformed grains in cooled metals with strain-free grains when heated. It differs from stress relief recovery. Recovery starts fast and slows down, while recrystallization starts slow, peaks and levels of subcritical temperatures are used for steel. Spheroidizing, depending on the time temperature exposure of a steel, the cementite carbides in a steel can form different morphologies such as lamellar cementite of ferrite or not to work, or a network of cementite along prior austenate grain boundaries in a hypoeutectoid steel. Normalizing steel increases grain size, improves structure and uniformity, increases hardenability, and improves machinability. When heated, carbon can diffuse while creating a uniform composition throughout the steel. To be properly classified as a normalizing treatment, the heating portion of the process must produce a homogeneous outstanding phase prior to cooling. Figure 9.25 compares the time temperature cycle of normalizing to that of fuel annealing. Next, 9.6 furnace heating and induction heating. Heat treatment of steel involves a wide variety of methods for annealing, normalizing, hardening, and tempering. Fuel-fired and electrically heated furnaces are used in a wide variety of configuration with various media. Furnace heating. Heat-treating furnaces can be generally classified as either batch or continuous furnaces. Batch-type furnaces, where loads are placed in the unit on the furnaces. The furnaces loads are brought up to a temperature together, and depending on the process, the furnaces may or may not be cooled before it is opened and the load removed. Continuous type furnaces, which operate in uninterrupted cycles as a workpiece pass over a stationary hearth and to the hearth itself moves. Induction heating is a method of heating electrically conductivity material by the application of a varying magnetic field whose lines of force enter the workpiece. In the process, the varying magnetic field induces an electric potential voltage, which can then create an electric current depending on the shape and the electrical characteristic on the workpiece. Other advantages of induction heat treating, which stem from this non-contact method and its generation of heat within the workpiece, are ease of automation and control, reduced floor space requirements, quiet and clean working condition, suitability for integration in a production line or general work area due to the elimination of secondary of radiant heating, self-monitoring capability. This picture is box furnaces. Picture 9.26 are a basic type of batch furnace, and this picture 9.27 more complex configuration allow for horizontal loading. Next, 9.7 hardening and tempering. Hardening of steel involves a three-step process of austenitization, quenching, and tempering. Sometimes an additional step of cold treating is done at low temperature below the melted side finish temperature of the steel. The quenching process is the rapid cooling of metal from the austenitizing or solution treating temperature, usually between 815 to 870 degrees Celsius or 1500 to 1600 degrees Fahrenheit. For medium and low carbon steels, to high temperatures such as 32 degrees Celsius or 2250 degrees Fahrenheit for high-speed steels. Quenching is used to produce martensite in the metal microstructure. The rate of heat extraction by a quenching medium and the way it is used substantially influences quench hand performance. Variations in quenching practice have resulted in the assignment of specific names to some quenching techniques. direct quenching, time quenching, selective quenching, spray quenching, fog quenching, interrupt quenching. Next, interrupt quenching refers to the rapid cooling of the metal from the austenizing temperature to the point above the means where it is held for a specific period of time, followed by cooling in the air. There are three types of interrupt quenching: auto-tempering, mild quenching, or mild tempering, and isothermal quenching. The temperature at which the quenching is interrupted, the length of time the steel is held at temperature, and the rate of cooling can vary depending on the type of steel and workpiece thickness. Comparisons of direct and interrupt quench cycles are shown in picture 9.35. Now 9.8 cool treating of steel. After hardening, some alloys retain a significant amount of austenite that does not transform to martensite. A good example of such a grade is D2 tool steel. It is not unusual for D2 to have as much as 20% retained austenite after undergoing standard heat treatment. Still, it is not completely transformed after hardening, can undergo cool treatment or cryogenic treatment to increase the transformation thrust. Cool treatment helps the transformation of austenite to martensite. However, it must be ensured that the steel and product design can tolerate direct cool treatment. Design features such as sharp corners and sharp changes in parts can trigger cracks. The cold treating method involves using a home filter to convert austenite to martensite at a temperature of about minus 18 degrees Celsius or minus 0 degrees Fahrenheit. Hardening testing can assess the effective finish of this cool treatment. Dry ice is also often used with a furnace temperature of minus 78 degrees Celsius or minus 109 degrees Fahrenheit and a room temperature of around minus 60 degrees Celsius or around minus 75 degrees Fahrenheit. Next, 9.9 Case hardening. Case hardening is a generic term used for several processes that put a hard, wear-resistant furnace a surface layer on a part. 9.9.1 Diffusion methods of case hardening. Case hardening, also known as a surface hardening, is a heat treatment process that increases the hardness of the outer surface of steel while keeping the core relatively soft. There are several methods used in case hardening, including carburizing. This is the most common method of case hardening, where carbon is added to the surface of the steel through a diffusion process. Nitrating. This method involves the diffusion of nitrogen into the surface of the steel. Nitrogen reacts with the steel to form a hard, wear-resistant layer. 9.9.2 Localized hardening processes. Localized hardening processes refer to technique used to create areas of different properties within a steel part. This involves differential heat treatment to harden or soften specific regions of the materials, resulting in varying levels of hardness and strength across the part. The process is particularly useful in applications where different properties are required in different areas of the part, such as in crankshafts where a tow core is needed for high cycle fatigue resistant and hardened surface is necessary for wear resistance. Next, induction heating occurs from induction eddy currents, which have a skin depth that depends on the variation frequency of the AC. Thus, the case depth of induction hardened parts can be varied by frequency and power. Figure 9.43. The higher the frequency, the thinner or more shallow the heating, the deeper case depths, and even true hardening are produced by using lower frequencies. Now, next 9.10, heat treating equipment. Heat treating equipment in metallurgy is equipment used to carry out heat treatment processes on metal. This process involves heating the metal to a certain temperature and then cooling it to change the microstructure and properties of the metal. The purpose of heat treatment is to increase the hardness, ductility, and ability of the metal, as well as reduce forming power requirements and energy requirements. Next, continuous furnaces, figure 9.48, are typically used for continuous volume production. Some types include roller-head furnaces, rising conveyor belt, pusher furnaces, shaker-head furnaces, and rotary retorted furnaces. A head roller furnace move goods with roll driven by moving devices. Conveyor belts are used in moving head furnaces. Pusher furnaces provide higher loads by using mechanical press. A shaker-head furnace moves items through vibration. Rotary return furnaces are used for heat treatment with uniform case hardening. I think I can explain. Can I explain? If there are an error in reading, please forgive me, and thank you for watching my video. And the last, Om Swastiastu.